Here's an example of a problem that uses the work-energy theorem and rotational motion. So the question is, a bike wheel is mounted on its axis and has a mass of 3 kilograms and a diameter of 90 centimeters. Constant force of 15 newtons is applied perpendicular to the surface of the wheel for 2 full rotations of the wheel. So the two parts of the question are, number 1, how much kinetic energy does the wheel have when you're done applying the force? And 2, how fast is it rotating? And so what we're going to do here is use the work-energy theorem. So the first thing to do is draw a picture of this so we can have some idea of what we're dealing with. So first off, we have our wheel, which is rotating about its axis right here, and the wheel has a radius of r and a force F is being applied to it. So now what we're going to do is use the work-energy theorem, and the work-energy theorem is that the work done is equal to the change in kinetic energy. And so the wheel is starting from rest, so we don't have to worry about that. So in that case, the work done is equal to the kinetic energy at the end, so KE final. And so in this case, work, because we're talking about rotational motion, is the integral of torque over an angle, so T dot d theta. And what we're going to be doing here is turning this wheel, and so you can see from the direction of the force that it's going to be rotating in this direction, and so the torque is going to be pointing in the same direction as the angle. So what we really have to do here is calculate the torque, and then we know what d theta is, and we know that the force is going to be constant, so the torque is going to be constant, and we can go from there. So let's calculate the torque. So torque, as we know, is R cross F. And so that just works out to, when we're talking about magnitudes, the magnitude of torque is just the magnitude of the radius, the magnitude of the force that's applied, times the sine of the angle between them. And we have to be a little bit careful about confusing sine theta, which is the angle in between the radial vector and the force, or the moment arm and the force, and the d theta up here, which is the number of revolutions. And so this is unfortunate, but it's about to go away because we can see from looking at our picture up here that the angle between the moment arm and the force is just 90 degrees. So sine of theta can simplify to 1, because the sine of 90 degrees is 1. So in that case, the magnitude of the torque, which I'm just going to write as a tau without a vector on it, is just the radius times the force that's applied. Okay, so now we have the torque, and we know it's RF. And so if you recall, work is just the integral of torque over some angle d theta. Now, in this case, the force is constant, so the torque is constant. And so all that means then is that this integral of tau d theta, simplifies down to the magnitude of the torque times delta theta. And that's the work that's done, so that's the change in kinetic energy. And so that is equal to the final kinetic energy, because initially it's at rest. So now we have to calculate T delta theta. We already calculated the magnitude of the torque up here, or the equation for it, and we know that delta theta is 2 revolutions, which means that there's 2 pi radians per revolution, so it's just 4 pi radians. And so the work that was done, which is equal to the final kinetic energy, again, it's only that because the initial kinetic energy is 0, is just going to be R times F times 4 pi. And when you plug all the numbers in, the diameter is 90 centimeters, so the radius is 45 centimeters, or 0.45 meters. The force is 15 newtons, so 0.45 meters. The force is 15 newtons, and 4 pi is 4 pi, so that's about 12 and a half. And so when we plug in all of our numbers and calculate, we get that the force is equal to 84.82 joules. Because remember, newtons times meters are joules. So that is our final kinetic energy. So then, that's the first part of the problem. And then the second part of the problem is once how fast is the wheel rotating? And so in this case, we can say the final kinetic energy, and I'm just going to write this as Ke sub f at the moment, is equal to, because it's purely rotational, 1/2 I omega squared. And so omega I is the moment of inertia, omega is the radial velocity, or I'm sorry, the angular velocity. And so for a wheel, which has all of its mass concentrated on the outside, the moment of inertia is just mr squared. So that just means that the final kinetic energy is equal to 1/2 quantity mr squared times omega squared. So if I'm going to simplify that, that means that omega, and so this is just taking this equation right here and solving for omega, what I'm going to see is that omega squared is equal to the kinetic energy, the final kinetic energy, over 1/2 mr squared. Or omega, take the square root of both sides, and it's just going to be equal to this number. So then when I go ahead and plug in all my numbers, remember the kinetic energy is 84.2 joules. I'm sorry, it's 84.82 joules. M is 3 kilograms, and R is 0.45 meters. When I plug all of this in to my expression up here, I see that omega, my angular velocity, is going to be 16.71 radians per second. And so that is how fast the wheel is rotating. Thank you very much.